We're going to find the coordinates of the stationary points on each of these curves. So we want to differentiate and make our gradient equal to 0. So first, y equals x times e to the 2x. So we need to use the product rule on this because I've got the product of two functions. I've got the x and I've got the e to the power 2x. So I'm going to say that my u is the x function and my v is the e to the 2x function. Differentiating x, I get 1. Differentiating the e to the power 2x, I need to use the chain rule on that because I've got the 2x inside the exponential function. So the exponential function will differentiate to be the exponential function, and then I have to multiply that by the derivative of the inside. The derivative of 2x is 2. Now applying the product rule to that, I've got u dash times v plus v dash times u. So 1 times e to the power 2x plus x times 2 e to the power 2x, which is going to simplify. And then I can factorise out the e to the power 2x to make it even simpler. And so I want to find the coordinates where this gradient function is equal to 0. So 0 equals e to the power 2x times the 1 plus 2x. I know for a fact that this exponential can't equal 0. The exponential never can. Remember, the exponential graph looks like this. It never passes through 0. So the only solution I can get here comes from here, when the 1 plus 2x equals 0, which is where x is equal to minus 1/2. So that's the x coordinate of my stationary point. To get the y coordinate, I want to substitute my x in here and here. So if I substitute minus 1/2 into both of those, then I find minus 1/2 times e to the power of minus 1/2 is minus 1/2 e to the power minus 1. And that's how I'll leave that answer in exact form. Next, we've got y equals x squared times 2x minus 3 to the power 4. So again, we're going to be using the product rule on this because I've got the x squared being multiplied by the 2x minus 3 to the power 4. So let's let my u be x squared and my v be 2x minus 3 to the power 4. When I differentiate x squared, I get 2x. Now, differentiating the v here, I'm going to have to use the chain rule for this because I've got the 2x minus 3 inside the power 4. So differentiate the power 4 first. So times by 4. Take 1 away from the power, and then by the chain rule I have to multiply this by the derivative of the inside. When I differentiate 2x minus 3, I get 2. And we can see that that's going to simplify here. The 4 times the 2 is going to be an 8. So I'm going to rewrite that in a slightly simpler form with an 8 at the front. Right, so let's apply the product rule then. So I've got u dash times v plus v dash times u. So 2x times 2x minus 3 to the power 4 plus 8x squared times 2x minus 3 to the power 3. And we can do some factorising here because we've got a 2 in both of these terms here. We've also got an x in both of these terms. And we've also got a 2x minus 3 cubed in both of these terms as well. So factorising all of those out, the 2x and the 2x minus 3 cubed, which will leave us on the inside with a 2x minus 3 from the first term and a 4x from the second term. And you could do a quick check here. You could do this times this is this, and this times this is this. We can then notice that this bracket here can be simplified a little bit, because we can collect those x terms together to be 6x minus 3. And then, even better, we can factorise another 3 outside here, because 3 goes into both of these terms here. So factorising a further 3 outside will make this a 6 now, and this a 2x minus 1. That is now in its fully factorised form, which is going to be really useful for the next bit where we want to find when that equals 0. Because I can now see clearly that this is going to equal 0 if 6x is equal to 0, or if 2x minus 3 cubed is equal to 0, or if the 2x minus 1 is equal to 0. Which happen at those x-coordinates. So those are the x-coordinates of my stationary points. If I now substitute each of those into my original function, into this up here, if I substitute 0 into that, so 0 squared times anything is just going to be 0. 3 over 2 squared times the 2 times 3 over 2 minus 3, that's going to be 0 as well. And then substituting the 1/2 into that, I get 4. So my coordinates of the stationary points here are 0, 0, 3 over 2, 0, and 1/2, 4. Part D. Again, product rule, because we've got the x being multiplied by the x plus 12 to the power of 1/2. So my u function is going to be the x, my v function is going to be the x plus 12 to the power of 1/2. Differentiating x, I get 1. Differentiating x plus 12 to the power of 1/2, I get 1/2. X plus 12 to the power of minus 1/2. Applying the product rule now then, so u dash times v plus v dashed times u. So 1 times x plus 12 to the power of 1/2 plus x times 1/2 times x plus 12 to the power of minus 1/2. I'm going to simplify this, so I'm going to take that negative power there and I'm going to write that on the bottom. And then I'm going to get a common denominator here, so I'm going to write that as a 1. And then I can see that I'm going to be multiplying the top and the bottom here of the first term by this 2 times x plus 12 to the power of 1/2. which means I have to times the numerator by that as well. So if I times the x plus 12 to the power of a half by the two lots of the x plus 12 to the power of a half, I'll have a 2 at the front. And the x plus 12 to the power of a half times x plus 12 to the power of a half will just be x plus 12, because the powers of 1/2 add together to make 1. Now I've got my common denominator, I can write these together as a single term, where I've got 2x plus 24 plus x, which is 3x plus 24. And that's my gradient function in its simplest form. For the stationary points, I'm going to make that equal to 0, which is going to be the case if the 3x plus 24 equals 0, which is going to be when x is minus 8. And for the y coordinate, if I take that minus 8 and substitute it back into this original function, so minus 8 times the square root of minus 8 plus 12 gives me minus 16. So that's the coordinate of the stationary point on y equals x times the square root of x plus 12.